Okay, good day everyone. First, let me introduce myself. My name is Bondan Swandi. I'm the first author of the manuscript, the paper with title BFT Watercolor Classification in Tilapia Aquaculture using Computer Vision. The registration number is 40074. As introduction, biofloc technology or BFT is one of the most developed technology which is considered as blue revolution in aquaculture. And the principle of biofloc is actually to convert and balance organic and inorganic compounds consisting of carbon, oxygen, hydrogen, and nitrogen into a mass of sludge in the form of biofloc by utilizing bacteria. As you can see in this figure, in the right side, this is the figure of biofloc that normally consists in an aquaculture pond. The color of the biofloc water actually indicates the dissolved content in the culture water, such as microbes and other components. This color can be used in estimating the condition of the BFT system and determining actions that should be taken afterwards. The BFT color that tends to be green indicates a high alga content, while a color that tends to be deep brown normally indicates a relatively high bacteria and floc content in the BFT water. The objective of our study actually is to classify the color of biofloc water automatically using the computer vision. So we capture photos by a camera that acting as a vision sensor. Sensor vision and computer vision technology are used to extract the RGB component from the color of the water, the BFT water, photos, and then used to analyze and classify. The classification stretches from the first conditioning phase of BFT aquaculture to the completion of the fish rearing cultivation phase. And more, the categorized photo will be linked with the interpretation of each of these classifications so that the condition of the BFT system can be predicted instantly using our proposed no-fill method. So in composing our setup, our experiment setup, first we make an aquaculture setup. We have a 12 BFT tilapia ponds that we use for 9 weeks cultivation, and each pond has 12 Larasati tilapia fish. This Larasati tilapia fish basically is a hybrid tilapia fish combination between the red tilapia and the black tilapia. We manage the temperature of our ponds maintained between 27.5 degree up to 30 degrees Celsius, and the pH also maintained between 7.74 to 8. In data collection setup, the water from the biofloc ponds is collected in a glass container. So each week we gather the water from the pond into the glass container. The glass container size is 20 by 20 by 30. It's a transparent glass container with a white backdrop. After that, the data image is collected. We collect the data by taking the photo using the SLR camera and a tripod inside a room with less light. We use a fixed parameter setup camera as can be seen in table 1, so we can assure that every week we have the same setup, so we can assure that in particular we have the same condition for each week we took the photo. After images were collected, we made some image data pre-processing. A cropping operation was performed in all of the data. We cut it into size of 175 by 175 pixel. In total, we got 120 data images. However, only 102 were qualified to be used in this research. In general, the workflow diagram of the experimental setup for the proposed method is shown in these images, in this figure. First, we have 12 BFT ponds. Then we make a water sampling. We put it in a glass container. We make an image data collection, the shooting setup. Then we pre-processing the image data. We cut it into the 175 and 175 pixel. And then we collect the data into the table. After that, we make a color classification using our proposed algorithm, our proposed novel algorithm. And when we know the color, the classification of the color, we can give an estimation of cultivation condition and also suggestion based on BFT watercolor to the cultivator. Before I go forward, I have to explain what is MCCI and how we interpretation the BFT color. MCCI, or the microbial community color index, actually is a color classification method of the BFT system developed by Kirk. So basically, the BFT system, the method is based on the ratio of the heterotrophic biomass to the autotrophic biomass. This calculation also represents the dominance of alga or bacteria in the cultivation water of the BFT system. As I mentioned before, when the water is green, it means alga are dominant. Meanwhile, if the water tends to be deep brown, it means it's dominated by heterotrophs. As you can see, the image here in the top right, this is the MCCI number generated by the formula that proposed by the Kirk. And using this result of formula, we can classify which categories of the color of the bioflow. Basically, to calculate the MCCI formula, we need to extract the red, green, and blue, or we know as RGB value, from the image color. Once we have the RGB value, we can calculate the MCCI formula using this formula in the bottom right, and then we have the value of the MCCI. The MCCI result score indicates 4 color categories. Start from deep brown, brown-green, green-brown, and green. So it has 4 categories. In our research, one of the drawbacks that MCCI SIM is that the formula, that MCCI formula, can only detect the color of bioflow cultivation water from green to dark brown. However, in our research, we found that in the week 0 through the week 2, we have the clear color. Here it's represented with the white color because we have the white backdrop. However, this one is a clear color one, and it's not represented by the MCCI formula. MCCI is unable to identify the clear color of the aquaculture water. However, monitoring the clear water color is also important for the cultivator. Why? Because it helps to analyze whether the bioflow cultivation water is developing as it should during the early period of the cultivation process. And also based on the reference from Hargreaves and Tau in our reference, we made a classification for the water cultivation of the BFT system, and it's shown in table 2. So here in table 2, we classified the water color, including the clear water color. We also made the meaning and the suggestion, what it should done and what is the meaning of the color. For example, if the water is clear, it means that it's in the early phase of the biofloc development, and it has small domination of alga and bacteria. Then we can suggest that the cultivator need to observe within 2 to 3 weeks. And if it's possible, it can be given the lower aerator power, the aerator water power. When the color start to become green, it means it high dominance of alga. Since the alga produce oxygen through the photosynthesis, in this phase, it has a surplus oxygen produced from the alga photosynthesis. It means we can set the aerator power into the medium, not the maximum, because there is another source of oxygen from the alga. When it starts to change color into the green bone, it means it still have higher dominance of alga, but it start small dominance of bacteria. So flock is start to develop. And we can make a suggestion to the cultivator that he can make some check of the composition of the flock, and still he can set the medium aerator power. Once the water start to be brown, green, and deep brown, it means the dominance of the water is dominated by the bacteria. It means it needs higher consumption of aerator power. It needs more power in the aerator. Why? Because bacteria didn't produce any oxygen. Even it needs more oxygen on it. That's why we can give suggestion to the cultivator to increase the power of the aerator. And we also can give suggestion when the water it's become deep brown, it means it's near final phase of the cultivation process. As initial analysis from the data that we collect, after 9 weeks of image data collection, we realized that from our data, only 2 MCCI color group can be defined, namely the brown-green, the deep brown, and also additional clear color in the first phase. There is no green and green-brown color were found. It means less alga development in the early phase. Why? We realized that our pond is placed in a semi-outdoor pond. Alga development will be affected in the early stage because our pond didn't receive enough exposed to the sunlight. Sunlight is one of the main components that needed by the alga to improve, to grow. That's why our biofloc system doesn't have any green color because the alga is not really developed in our system. In table 3, using the MCCI value, we also make the classification of the color that we made, which is the deep brown, brown-green, and the green-brown and green. Now we go to the explanation of our proposed novel algorithm. So to classify the color of the BFT watercolor, to make it automated, we propose 2 novel algorithms. The first one is the black and white and the MCCI classification. So the first method has 2 phases, the clear data process phase, and the second one is the MCCI data process phase. In the clear data process phase, first we classify whether the color is clear or color. So just between 2 phases, clear or color. That's why we only need a black and white algorithm. So the watercolor data set, we convert it into black and white image, we convert to RGB format, and then we calculate whether the image is colored or not. If it's not colored, then it's clear data set. When it's colored, it means it's go to the MCCI dataset. And the second phase, MCCI data process. So the dataset that we get from the first phase, the MCCI dataset, we know that this is the colored one. Then we process it in the RGB data format. We calculate the RGB mean, and then we calculate the MCCI algorithm from the color. Then after we get the MCCI value, we classify the color based on the range of the value. So we can get the brown-green category, the deep brown category, the green-brown category, and the green category. The second proposed novel algorithm, we use the Manhattan distance algorithm. Actually, we might say this is a simple form of machine learning algorithm. Why? Because in this algorithm, we need to train the system. So we have to divide the dataset into two datasets. The first one is the training dataset, and the second one is the test dataset. So this algorithm needs initial classification and data training. The training dataset is made up of image of BFT ponds from ponds A and pond B. From this training, we will get the anchor data point. This anchor data point will be the anchor for the classification of the color. And for the testing dataset, we include all of the data that we get from our research. So as the diagram flow of the algorithm, once we have the dataset, we split the data into the training and the test dataset. From the training dataset, we train the algorithm, and then we get the anchor point for each classification. Once we get the anchor point from the test dataset, we can classify using this Manhattan algorithm whether this image is classified as a clear color or green-brown or deep brown. As a result and discussion, from the first method, the classification of clear image using black and white and MCCI algorithm, we can see that in the clear dataset process, there is 2.8% of error. So from 36 data clear, it can only detect 35. And in the MCCI classification software, there is error of brown-green 9% and deep brown of 4 or 5.8%. And as the result of the second method, the clear brown-green and brown color category produce 0%, 6% for the brown-green, and 0% from the deep brown. In the brown-green category, the 6% error occurs shows the closeness of the data value toward the clear color category. So it's a bit ambiguity. Which color should be clear or brown-green? Even with the naked eye, it's difficult to differentiate. And to conclude, we can say that water classification using computer vision is possible to be done in the BFT Tilapia aquaculture system method. It's able to identify the BFT color phase from the clear color until the end of the cultivation process, until it gets brown. Result from both methods demonstrate that the result error in classifying the BFT color system was still within our tolerance limit, which is 10%. So we can use both. We can see that second method, or Manhattan distance algorithm, yields more promising result than the black and white and MCCI classification, or the first method. However, the first method is adaptable in varied cultivation conditions. Why? Because it doesn't require initial classification and training process. So when you move into other environment, you don't have to make a new training for your algorithm. You just put and run the algorithm of the first method. Of course, further development is also possible. We need to improve our total data sample. We need to improve our training data set and introduce more dependable procedure in accordance to the system required. Thank you very much. This is end of my presentation. I hope you enjoy our research.